Kubernetes pods come with several advanced features that help in managing their lifecycle, placement, and stability. Here's an overview of some key advanced features such as health probes, affinity, anti-affinity, tolerations, and more. 1. Health probes. Readiness probe. Used to determine if a container is ready to start serving traffic. If the readiness probe fails, the pod is temporarily removed from the list of endpoints that can serve requests. Helps in controlling traffic flow and ensuring that only healthy instances receive traffic. Liveness probe, used to check if a container is still running. If the liveness probe fails, Kubernetes will restart the container, helping recover from failures. Can be configured to check application health through HTTP requests, TCP connections, or executing commands within the container. Startup probe, used to detect whether an application has started successfully. If the startup probe fails, Kubernetes will continue to restart the container until it succeeds, especially useful for slow-starting applications that may need additional time to be considered started. 2. Pod affinity and anti-affinity. Affinity allows you to control which nodes a pod should be scheduled on based on labels and other criteria. Node affinity enables scheduling pods on nodes that meet specific criteria, such as certain hardware characteristics or custom labels. Similar to node selectors, but offers more flexibility with soft, preferred, and hard, required rules. Pod affinity allows scheduling of pods close to other pods with matching labels, which is useful for applications that benefit from proximity, e.g., communication-intensive microservices. Anti-affinity ensures that certain pods are not scheduled on the same node or within a specific topology, e.g., availability zone. Useful for high availability applications where redundancy is required to prevent a single point of failure. 3. Tolerations and taints. Tolerations allow a pod to be scheduled on nodes with specific taints. Tolerations specify that a pod can tolerate the taint applied to a node which would otherwise prevent it from being scheduled there. Commonly used for workload segregation, such as running specific workloads on dedicated hardware. Taints, applied to nodes to repel certain pods. Work together with tolerations to control pod scheduling based on node characteristics. Pod disruption budgets, PDBs, ensures availability during maintenance. Allows you to specify the minimum number of pods that must be running during voluntary disruptions, e.g., node upgrades. Helps maintain the availability of critical applications while performing cluster maintenance or scaling activities. Settings include minimum number of available pods, maximum number of pods that can be disrupted simultaneously. 5. Resource requests and limits. Requests specify the minimum amount of CPU and memory resources required for a container. Helps Kubernetes make better scheduling decisions by ensuring that the pod is placed on a node with sufficient available resources. Limits define the maximum amount of resources a container can consume. Prevents a container from consuming too many resources, ensuring fair distribution among other containers. 6. Init containers. Special type of container. Runs before the main application containers start. Used to perform initialization tasks, such as setting up configuration files or waiting for a dependency to become available. Sequential execution. Init containers are executed sequentially, and the main application containers only start once all init containers have successfully completed. 7. Sidecar containers. Auxiliary containers. Run alongside the main application container within the same pod. Provide support functions, such as logging, monitoring, or proxying requests. Common patterns. Log aggregation. Collects and ships logs from the main container. Service Mesh Sidecar. Injects network proxies for managing inter-service communication, e.g. Istio or Envoy. 8. Ephemeral containers. Debugging containers. Temporarily added to a running pod for debugging purposes. Can be used to troubleshoot issues without restarting or modifying the existing pod. Non-persistent. These containers do not survive pod restarts and are not part of the original pod specification. Non-ag pods. Manually created pods, defined directly on a specific node, not managed by the Kubernetes API server. Useful for system-level components, often used for deploying essential services, such as network plugins or monitoring agents that need to be tightly integrated with the node. Our summary. These advanced features allow Kubernetes to manage pods with greater control and flexibility. Health probes ensure that applications are running properly, while affinity, anti-affinity, and tolerations provide sophisticated scheduling options. Pod disruption budgets, resource limits, and sidecar containers enhance stability and resilience, making Kubernetes an effective platform for running complex and mission-critical workloads.